All right, so section 6.1, part 1, estimating with finite sums. Okay, so sigma notation. Have you guys seen sigma notation before?
I hate this. I hate literally the worst thing in math.
It's not.
I'm so excited.
All right, the sum of n terms. So if I have a1, a2, a3, all the way to an, you would write it as sigma I equals 1 to n. So the bottom number is where you start. So the I equals 1 is start there. The top number is where you stop. I is called the index. A sub I is called the ith term of the sum. 1 is the lower bound. And I is the upper bound. Or n is the upper bound. So write the following in expanded form. So you can have anything. I mean, it doesn't have to be I. It can be I, K, J. These are the usual things you'll see. I, J, and K. All right, so if I have I equals 0 to 5, 2i plus 1, this means plug in 0, plug in 1, plug in 2, 3, 4, and 5, and then add all those different things together. So I'm going to have 2 times 0 plus 1, plus 2 times 1 plus 1, plus 2 times 2 plus 1, so I have 1 plus 3 plus 5 plus 7 plus 9 plus 11, odd numbers. So you get 36. So 36 should be your answer. All right, so this one's a little bit different. This time I have n and k. So it says start with k equals 1. So for all the k values, you're plugging in 1, then 2, then 3, then 4, and you're stopping with n. Okay, so this one would be 1 over n times 1 squared plus 1, plus 1 over n times 2 squared plus 1, plus 1 over n times 3 squared plus 1, dot, 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 plus 1 over n times n squared plus 1.
Is this just expanded form, so we're just plugging?
Yep, we're just writing expanded form. Yep.
Okay.
So n could go to anything. N could be a million. All right, so you can kind of simplify this. Do you guys see how you could just pull out the 1 over n? They all had 1 over n in common. So pull out a 1 over n. It's like the reverse distributive property. So then I'd have 1 squared plus 1, so 2, plus 5, plus 10, plus dot, 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 n squared plus 1. I usually leave that in parentheses so you can see that's all one number there. Okay. Make sense? Can't really simplify it much more. All right, so Gauss rhymes with mouse. Remember him? So Carl Friedrich Gauss, he's German, so it's much more like throaty. I don't know if anybody can do like
Nice.
German.
Gauss.
Yeah. Good job, Allie. All right, he's a famous mathematician. He was a child prodigy, but he was kind of a little punk. We talked about this in algebra too. So he got in trouble a lot. So the story goes a couple different ways. So one story is that he just got in trouble and he was asked to go to the corner and he had to add up all the digits from 1 to 100. And then once he was done, he was allowed to rejoin the class. That's one story. The other story is that the whole class was in trouble. And so the teacher just wanted some peace and quiet and was like, okay, well, for the next 30 minutes, you guys need to add up all the numbers 1 to 100. And he's 10, so that's going to take a while, right? But he did it right away. And the teacher was very annoyed with him and was like, you don't have the answer. That can't be the answer. You know, she didn't know what it was. So how did Carl Friedrich Gauss do it? There's pairs. How many pairs? If I have 100 numbers, how many pairs? 50 pairs. 50 pairs of 101. So he did 50 times 101, which he could actually do with the distributive property if he was really good. So it's 5,000 plus 50. So it's 50, 50. Okay, so in Algebra 2, you guys learned that formula, which was n over 2, so that's your number of pairs, a1 plus a sub n. So I always call that the Gauss formula. It's a finite sum of an arithmetic sequence. That's what you'd technically call it.
What is the little touchy bouncing
What's the what?
A1 plus
A sub n. My n's are weird. Okay, so our summation formula, so let's think about it. So c is a number, so c is a constant. If I had I equals 1 to I equals n, that means I'm plugging in 1, then 2, then 3, but I can't really plug in because c is a constant. It's like adding 5. How many times do I add it? N times. So you would have c plus c plus c plus itself n times. So if you were summing a constant n times, it would be c times n. Cn. Okay, so let's go to the right. So if I have I starting at 1 and going to n of I, so the sum of all the I terms, that means I'd have 1 plus 2 plus 3 plus dot 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 n. Well, that's what we just did. That's the Gauss formula. So there'd be n over 2 pairs times 1 plus n. In other words, n squared plus n all over 2. All right, so last here, kind of random. So I squared is going to be n times n plus 1 times 2n plus 1 all over 6. Yeah. See if I have to look it up. Yeah, I'd give these two to you. All right, and then I cubed. I cubed is n squared times n plus 1 squared all over 4. These won't be on your final, by the way. So. All right, so use the summation formula to find the sums. Verify with your graphing calculator. Okay, so if I have I equals 1 to 10, think about what you're doing. So you can write out the first few terms if you really need to see it. So if you really needed to see what was going on, it would be 1 squared minus 1 plus 2 squared minus 1 plus 3 squared minus 1. Does that make sense? So think about how you could break it apart. Do you see that you could do the sum of all the squareds? And then you have minus 1 how many times? 10 times. So you can think of it as minus 1, I equals 1 to 10. So those are your two different summations. It's like you're separating all of the pieces. Do you see what I'm saying? So it's like I'm rewriting it so that I see 1 squared plus 2 squared plus 3 squareds, so all the squareds, and then I have minus 1, minus 1, minus 1, minus 1, and so on, 10 times. Okay, that's when you can use those formulas. So if I have the sum from I equals 1 to 10 of I squared, I'm using this formula. So I'm going to plug in 10. So I'd have equals 10 times 10 plus 1 times 20 plus 1 all over 6. And then minus, we said the other one was 10.
Can you also do the Gauss one with 9? Because you're like, if for some reason 0.
No, because this isn't what we call an arithmetic series. Like you can't use Gauss because you're not always adding a common difference. Like you'd had 1, 4, 9, 16. It's not always adding the same amount each time. So you can only do the Gauss with a common difference. So I have 10 times 11 times 21 divided by 6. So I have 385 minus 10. So I get 375. Okay, next one. Okay, so think about what you could do here. Do you see they have a 3 over 100 in common? all of them would have a 3 over 100. So think of all your individual terms having a 3 over 100. You could pull that 3 over 100 out to the front. So you're going to have 3 over 100, and then the sum of all the terms, I squared plus 1, oh, no denominator. So I'm going to find the sum of the I squared plus 1, and then I'm going to multiply by 3 over 100.
Is the 100 on top of the sum?
Oh, it's 100, thank you. Yep, do you guys see how I did that? Do you want me to write the step in between?
No.
Okay. All right, so I have my 3 over 100. I'm going to have the sum of I squared plus, what am I going to add on? Yeah, plus 100, because it's going to be the sum of 1 100 times. Okay, so we use that formula again. So I have my 3 over 100. In my formula, if I have my I squared, I'm going to have 100 times 101 times 201 all over 6 plus 100. So you should get, I'm going to write really small, 10,153.5. I know it ran off. So 10,153.5, 10153.5. Yes?
So you get an exact answer like that, should you put 3.00?
Nope. So on the AP test, you always have to do 3 decimal points, but if it's an exact answer, so it came out as 0.5, you can just write 0.5. All right, so notice how it says verify with your graphing calculator. So now I'm going to show you how you can use your graphing calculator.
I think I hate this because I can't draw the E well. It just looks really ugly.
That makes sense.
Find it. Okay, so to get the sum, you're going to do second list, arrow over to math, and then number 5. And then you want to put in what you're trying to take the sum of. So in our case, for number 1, let's do x squared minus 1, comma. And do you remember how we did end derivative? We always have to put x. So do x, comma, and x is going from 1 to 10. Oh, maybe we don't need to do the x. No, I'm going to mess it up.
Don't you have to put it in sum then sequence?
I think you're right.
Yeah.
It was something.
Mine always has the fancy one.
Sum and then sequence. Is that right?
Wait, what?
This will be
Just wait. Okay.
some sequence.
Okay, gotcha.
X.
Okay, so sum and then sequence. Thank you, AP stats people. All right, so you're gonna, for this first one, so you're gonna do sum, sequence. It's right next to the sum, so go back through. So you need to put it in like that. Oh, let's see. Operations. It's not under math, it's under ops. So second list, list, ops. Complicated, isn't it? Seems like it's easier just to, use those formulas. Yeah. All right, makes sense?
Yeah, but that's out of order.
It's out of order.
Should it be second sum?
It should say sum seq.
Yeah, never mind. Yeah, that's right.
Okay, so you can do the other one. You should get 10,153.5.
Oh, heck.
Give Nick a point for helping me out there. All right, so at the bottom it talks about Archimedes. So we did that activity at the beginning of class with Archimedes. Okay, So suppose you have the curve y equals x squared, and you want to find the area between the curve and the x-axis from 0 to 2. Do you guys remember at the very beginning of the year we did this? Those overestimates, underestimates? All right, so if I have x squared from 0 to 2, we're going to divide it into 4 rectangles. So we're going to have S1, S2, S3, and S4 as our strips. Those are going to be at 1/2, 1, 3/4, not 3/4, 1 1/2, 3/2, and 2. So find the area of each rectangle using right endpoints. So right endpoints, that means I'm going to take my right points. So if I want to do the first strip from 0 to 1/2, I'm going to go on the right side, so with 1/2, and I go straight over. Okay, now the next strip on the right side is 1. So start at 1, go up, straight over. The next strip, the right point is 3/2, so go straight over. And the last one is 2, so straight over. This is called the right-hand sum, and we call it R4. Now your book likes to call this the right rectangular area, or approximation method, RRAM. So you can call it that, or you can just call it R4. In this case, this is an overestimate. Now the question is the right-hand sum always an overestimate? No. Like on the other side, if I went from -2 to 0, it would be an underestimate. Do you guys see that? Because then all my right sides would be underneath. Okay, and sometimes it's neither. So think about when it would be neither. If your curve went up and then back down, if you were doing right-hand estimates, at first it's an overestimate. But then all of a sudden your right hand is an underestimate. Yeah, so it doesn't necessarily have to be an overestimate or an underestimate. Okay, so my right-hand sum with 4 is going to be, I have a 1/2 for my width, and I have 1/2 squared. Plus 1/2 is my width, and then I have 1 squared for the next one. 1/2 is my width, and my height is 3/2 squared. Do you guys see where I'm getting the squared? It's from my y values. So this first y value would be 1/2 squared, it'd be 1/4. This next value would be at a height of 1, so it'd be 1. The next y value would be 3/2 squared, so it'd be 9/4. And the last y value would be 2 squared, so it'd be 4. So it's your y values. So whenever you're talking about the area of your rectangle, you're doing your width, which is 1/2, times the height. So width times height gives that first one. So do you see the 1/2, the squared now? Because it's from your original as x squared. So that x value was being squared to get the y value. Okay, so I have 1/2. I'm going to pull the 1/2 from each one. So I have 1/4 plus 1 plus 9/4 plus 4. On the AP test, almost always, it's not an even interval. So notice how all of ours had a width of 1/2. A lot of times they're going to give you tables, and those tables don't have nice even intervals. So they're not always going to be 1/2, so you can just pull it out to the front. So I have 1/2 times 7.5. So I get 3.75. Okay, so we can complete the same process to find the left-hand sum, which is an underestimate. And then how are these values related to the original value, or the original area? So one would be under and one would be over. And then you could take the average of the two to get a more precise measurement. Make sense? Okay, then we can use 10 strips. So we'll do that next time.